Okay, this is a short video on the ideal gas process problem that we did in workshop the other day, and we didn't get quite through it, so I thought I would go through the solution to all the problems and give a bit more of an explanation for you guys. So the problem is the following. We have a certain ideal gas process shown in the graph on this first page. So in this process we move from around from three different states. We move from state A to state B to state C via the graph as shown on the graph. So this is called a Herring cycle. And we start at A, we move up to state B, and if you notice that process, we're just changing the pressure of the gas. We're not changing its volume. So as we move from A to B, that's an isobaric, not isobaric, it's isochoric process. Right, an isochoric process is a process where we keep the volume constant. Now let's look as we switch from state C to state A. In that state we keep pressure constant, but the volume changes. So that part of the process is isobaric, or constant pressure. As we move from B to C, it's not really an isothermal process, because remember, for an isothermal process we keep temperature constant, and the kind of curve that we follow to go from state to state is a hyperbola, where here we just have a straight line. So this part of the process doesn't have a name, so we'll just call it no name. Okay? Alright, so what we're going to do is answer all of the all of part one for this Herring cycle. And some of the things we're going to find, first of all, we're going to find all the state variables for each of the different states, so it's state A, B, or C. We're also going to find the thermal energy at each state, and then we're going to figure out the work done by the gas to get from one state to the other, and we're also going to find the change in the thermal energy as we move from one state to another. And finally, for part one, we're going to find the heat added to the system to get from one state to the other. Okay, so let's go to the next page here. Now basically we're going to fill up these two tables. Now I've already inputted some of the information from the graph, so all the numbers there in red represent the pressure and volume at the various states. And one other thing we were given in the problem, I'll go back to the first page, was the initial temperature, or rather the temperature at state A is 300 Kelvin. Alright, so let's go back here. Now the easiest thing to do right now is to get a value of N. This guy right here. So little n here is the number of moles of the ideal gas we have. And if you look at state A, we have 3 out of the 4 state variables. We have pressure, volume, and temperature. So we actually have enough information to get the number of moles quite easily. So I have a blank page over here, and we can go right to the ideal gas law, which is PV equals nRT. And we want to get our hands on that little n. So we can solve for little n. Little n is pressure times volume over RT. Now our pressure at state A is the 1 times 10 to the 5 pascals. The volume was 2 meters cubed. R is our constant. It's 8.31, and it has units of joules over moles times Kelvin. And finally, temperature was given to be 300 Kelvin. Alright, so that is those are our numbers. We can plug those in our calculator. Into 3 sig figs, you should get 80.2 moles. Okay, so that's the number of moles of our ideal gas. So up back in table 1, I can insert 80.2. Now, the number of moles doesn't change as we go from state to state. So the number of moles in state A is 80.2, and same with state C. Okay? So that's our number of moles. And now if we look at state B and C, again, we know 3 out of the 4 state variables, so we can use the ideal gas law to find our new temperature. Or you can use the fact that the ratio PV over T is equal to a constant. And that's the constant, a number of moles times R. So if we look at pressure 1 and pressure 2 and pressure 1, volume 1, and temperature 1, they're going to equal the pressure at another state times the volume at that other state and the temperature at that other state. And so we can use these two this equation here to figure out various quantities. For example, as we move from state A to state B, we keep the we keep the volume constant. So V1 and V2 are the same, and we can simplify the equation, and we end up with P1 over T1 is equal to P2 over T2. Okay? So then we can rearrange this to find T2, or the temperature at state B, and that's just going to be P2 over P1 times T1. Okay? And so pressure, obviously P2 is 5 times 10 to the 5 pascals. The pressure at state 1 is 1 times 10 to the 5 pascals, and of course the temperature is 300 Kelvin. Okay, well, if you do all of that, you should get 1500 Kelvin. Okay? So the temperature in state B is 1500 Kelvin. So up here I can enter 1500 Kelvin. And I can do the same derivation to get the temperature at state C. What you should find, and you should check this yourself, is you get 900 Kelvin. Okay? So now we have all of our state variables for our ideal gas at state A, B, or C. All right, what's left to do for table 1 is to figure out the thermal energy. And we have a nice equation for thermal energy. I put this on the board last week, and the thermal energy of an ideal gas is of course related to the number of moles of the gas as well as the temperature. So we have this equation that E thermal is 3/2 times the number of moles times R times the temperature. So for example, for state A, we know the number of moles is 80.2. We know R is 8.31 joules per mole Kelvin, and we have temperature being 300 Kelvin. You plug all this in, all these numbers in your calculator, simplify the units, and what you should find is that the thermal energy is 300,000 joules. Okay? So that is our thermal energy at state A. 300,000 joules. And in fact, to get the thermal energy at state B and C, it's exactly the exact same formula, just our numbers change. And what you'll find, and you should check this yourself, at state B the thermal energy is 1,500,000 joules. At state C it's 900,000 joules. Alright, so that is our table 1. Let's go to table 2. So now we're asked the name of the process as we move from A to B, B to C, and C to A. I already went through this, so remember, go from state A to state B. That was an isochoric process. There was no name for this process, and for moving from C to A was an isobaric process. Okay? Now, let's look at this W here. So let's look at this line of table 2. That W, in our notes, that W is the work done on the gas, but if we go back to what we're asked in the question, we're asked for the work done by the gas. So that's slightly different. So I'm just going to change this variable to be W gas. Okay? Now, how do we get the work done by the gas? Well, we can get that directly from the graph. Remember, the work done by the gas in a process is the area under the curve. So if we look at the curve from A to B, that's a straight vertical line. There is no area under the curve for there. So the work done by the gas in an isochoric process is always 0. Okay? So now what about as we move from B to C? Well, there we have to calculate an area. So why don't I redraw that graph roughly down here. So we have our PV diagram, and as we go from B to C, we lose pressure and gain volume. Now the pressure at B was 5 times 10 to the 5. Oops, that's a 10 there. The pressure at C is 1 times 10 to the 5 PA. And of course volume increases from 2 meters cubed to 6 meters cubed. Okay, so what we want is the area under this curve. And what's convenient here is that we can, oops, that should be a dashed line. What we can do is calculate the area in 2 parts. First, we can calculate the area of this triangle, and then we can calculate the area of this rectangle. So the work done by the gas is first we calculate the area of the triangle, so that's 1/2 times the width. So the width is going to be 4 meters cubed, and then times the height, which is 4 times 10 to the 5 pascals. So that's just the area of the triangle. We also have to include the area of the rectangle. So that is, again, the width is 4 meters cubed, and the height now is 1 times 10 to the 5 pascals. Good. So we plug these numbers in our calculator, and note that a meter cubed times a pascal is a unit of energy, or joules. We get the value of 1,200,000 joules. So that's the work done by the gas as we move from state B to state C. So we can plug in 1,200,000 joules. Okay, so what about the work done by the gas as we move from state C to state A? Well, that's just the area of this rectangle here, which is this term we've already used. And what you'll find is that is, well, it has a magnitude of 400,000 joules. So this is equivalent to 400,000 joules. But the work done by the gas is going to be negative because we're actually losing volume. This is, as we go from C to state A here, we actually lose volume, so that's going to be negative work. So that's the work done by the gas as we move from C to A. So I can go back to my table and enter negative 400,000 joules. Okay? Alright, so that's that line of table 2. What about the next line, the change in the thermal energy? Well, this is actually rather straightforward. We can use the data from table 1. So as we move from A to B, we increase our thermal energy. We go from 300,000 to 1,500,000. So we increase our thermal energy by 1,200,000 joules. Okay, so what about as we move from B to C? Again, we just look at the final thermal energy and subtract the initial, and if you notice, we actually decrease the amount of thermal energy. We end up losing 600,000, so it's negative 600,000 joules. Similarly, as we go from state C to state A, we lose another 600,000 joules. Okay. So that is the change in the thermal energy as we move from one state to the other. Now what about the last row here, Q? So Q is the heat added to the system. To get that, we can go to our first law of thermodynamics, which says the heat added to the system is equal to the change in the thermal energy of the system plus the work done by the gas or by the system. And if we look at the right-hand side of this equation, we already have those two terms in our table 2 for each process. So let's look at the first column as we move from A to B. We basically add 0 joules and the 1,200,000 joules. So Q, the heat added to the system as we move from A to B, is 1,200,000 joules. As we move from B to C, again, we just add those two, add the work done by the gas to the change in the thermal energy, and we get 600,000 joules. And finally, as we move from state C to state A, we add the minus 400,000 to the negative 600,000, and we get negative 1 million joules. Okay. So that's table 1 and table 2. Let's look at the next part of this activity. So part 2. And now we're going to look at the entire cycle. So in part A, we're asked to compute the net change in the thermal energy of the system. So to get this, all we do is we look at we add the third line here of table 2. We have 3 changes in thermal energy, and if we add these all together, you know that they add to 0. So the net change in the thermal energy is 0 joules, and this makes sense. As in our cycle, we go from state A to state B to state C, and then back to state A. So when we're in state A, we should be back to the same thermal energy we started with. So this 0 joules does make sense. Let's look at B. The first part of B says how much heat is absorbed by the system. Well, we just look at the two positive terms here, Q. Remember, a positive Q represents heat added to the system, and a negative Q is, well, heat taken out of the system. So the heat added to the system is this 1,200,000 plus 600,000, and that's 1,800,000 joules. And how much heat is exhausted by the system? Well, that's the 1 million joules as we move from C to A. So that's 1 million joules. And to compute the net amount of heat transferred from the environment to the system, well, we just subtract 1 million from this 1,800,000, and we get 800,000 joules. Sorry to cram that in there. Okay, so let's look at part C. We want to compute the net amount of work done by the system on the environment. Okay, well, here we go to the this line of table 2. We look at the work done by the gas, and again we just add all of those works together, and so we have 1,200,000 plus negative 400,000, and that gives us 800,000 joules. Okay, so this number is not surprising that it's the same as the net amount of heat transferred from the environment to the system. So that heat gets used up as work. Okay, so these two numbers should be the same. And finally, part D, we want to determine the overall efficiency of the cycle. For this, we look at the heat added to the system, so the 1,800,000. So we have 1,800,000, and in the numerator we put the work done by the system. So that's the 800,000 joules, and what we get is a percentage. We get 0.44. So that is the overall efficiency of the cycle. The heat added to the system, it relates the heat added to the system with the work done by the system. Okay, so that is the solutions to all the questions on this activity. I hope this has been helpful, and I hope all this was understandable.